Well friends, welcome to the basic law of thermodynamics. So, those who are directly jumping into this lecture, the past lectures parts, what we saw was, we saw zeroth law, first law, second law. When does a first law exist or valid? When is it invalid or what is the limitation? Then we move to the second law of thermodynamics, wherein we saw about Kelvin Planck's statement, then we saw Clausius' statement, then we also moved into reversible, irreversible processes. And while going through the journey, we saw different cycles, we saw Carnot engine, then Otto cycle, Diesel cycle, Rankine cycle and Brayton cycle. Very fundamentally we saw those things. And finally, why did we see all those things is to find out the efficiency of the process. From that knowledge, we will move to lecture under basic law of thermodynamics. So, here in which we will try to see about perpetual motion machines, which is otherwise called as PMM. So, henceforth during the lectures, I will try to call it as PM or PMM. Right. So, then we will try to see the third law of thermodynamics, then exergy. So, energy ENERGY. So, ERGY is taken and X is added to it. We will see why is it added in the lecture. What is a PMM machine or what is PMM? A PMM refers to an imaginary machine which does not exist, that can operate endlessly without any energy input while continuously producing an useful output. So, you do not give any input, but the machine starts moving of its own, right. So, those machines are called as perpetual machines. Such machines have fascinated inventors for centuries, but they are fundamentally impossible because they violate the basic law of thermodynamics. So, now it is very clear that basic law of thermodynamics exists. If the basic law of thermodynamics is defeated, then it is always a perpetual machine. The concept of PMM reinforces the importance of the first and the second law. Energy is converted from one form to the other. The second law is all the energy which is converted, you will never try to convert all the energy into another form. So, that is what is told in the second law and reminds us that no energy system can be perfectly efficient or run forever without fuel or energy input. Think of a scooter you buy, a car you buy, you fill it once and then you forget it. So, rest maybe it runs for all through your lifetime, no petrol requirement, wonderful, right, but that does not exist. If that could exist, then laws of thermodynamics fail. So, that is what I have written here. No energy system can be perfectly efficient or run forever without fuel or energy input. PMM are classified based on thermodynamics laws. They attempt to break PMM 1 and PMM 2. There are two laws. What is PMM 1? PMM 1 violates the first law of thermodynamics, which is the law of energy of conservation. PMM assumes that it can produce more energy than it consumes, essentially creating energy from nothing. So, this is PMM 1, this is surrounding and you have a shaft. So, nothing is there, you do not give any input, it starts rotating. There can be a possibility, what if I make the surrounding very violent? For example, I pump in lot of air or I keep it on my terrace where there is a wind velocity. And friends, if you keep moving from floor to floor to floor, suppose you are staying in the 25th floor, 30th floor, the wind velocities are pretty high. Right. So, if you take this machine and go there, maybe you attach a fan here, so that the fan keeps rotating. But there also if you see, the wind velocity is somebody created. right. So, for example, a device that supposedly powers itself while running a generator without any fuel input would be a PMM1 condition. This directly contradicts the principle that energy cannot be created or destroyed in any physical form. This directly contradicts, because without anything you are able to get an output. PMM2 violates the second law of thermodynamics. It assumes that it can completely convert heat into work without any loss or heat rejection to a sink. 100% heat, 100% you try to convert it into work. It would be lovely if the turbine blade works, if the turbine machine works at 100% efficiency, nothing better than that, right. So, you will save lot of energy. If you take a thermal power plant, what we do is we put coal, we burn the coal, and then this generates lot of heat. This heat is transferred to water. This water gets converted into vapor, steam, and then from that steam is with great pressure, it is pushed into a blade. This blade starts rotating. Moment the blade starts rotating, there is a shaft which is attached, and this shaft is again attached to a generator, they draw. So, what if one time you put or 100% whatever you throw in gets converted, it will be lovely. So, you do not have to burn more coal. If you do not have to burn more coal, you do not have to excavate more coal. You see, the nature is getting protected if we have PMM2. It assumes that it can be completely convert heat into work without any loss or heat rejection to a sink. Hence, it would mean operating at 100% thermal efficiency. It is impossible because every real heat engine must reject some portion of absorbed heat to a cooler reservoir, and some energy is always lost due to irreversibility and increase in entropy. We saw increase in entropy in the last lecture. We were talking about S. S is nothing but the randomness created or the distortion whatever is created. Despite countless attempts, no perpetual motion machine has ever worked or been validated by scientific testing. Though people do, you see lot of WhatsApp small videos, or people have demonstrated PMM in a very incubated condition. All these things are there, but it is never demonstrated very successfully. These machines serves primarily as thought experiments to reinforce the strict boundaries set by the laws of thermodynamics. So, what are we trying to say? Thermodynamics laws cannot be violated, right. There is no machine developed violating the two laws. Their failure highlights an essential truth: all real systems require energy input to function and subject to inefficiency. So, is that clear? So, why are we talking more and more and more? This is because you should understand there is a lot of waste energy generated in any machine, and you will never be able to get 100%. So, moment you do not get 100%, to operate the machine, you will pump in more energy. So, to pump in more energy, you will have to generate that energy. You see, it is a cycle, right. So, all real system requires energy input to function and are subjected to inefficiency. So, there is always a loss. So, a heat source, then you have PMM2, then you have a surrounding. What is the third law of thermodynamics? We saw zeroth law, first law, second law. Now, we will see the third law of thermodynamics. Third law of thermodynamics deals with the behavior of the system as they approach absolute zero temperature. What happens at absolute zero? And it provides a reference point for the measurement of entropy. Only for this, the third law comes into existence. The law states that the temperature of a perfect crystalline substance approaches absolute zero, its entropy approaches zero as well. Generating perfect crystalline substance is difficult. We have covered in our materials portion what is crystalline, what is amorphous material. There are crystalline, semi-crystalline and amorphous material. So, perfectly crystalline substances approach 0, its entropy approaches 0 as well. So, as and when the decrease in temperature happens, there is a decrease in kinetic energy. More decrease in temperature, more decrease in kinetic energy. Kinetic energy is what? Potential energy, the leading to kinetic energy. Kinetic energy is basically half mv square, right. So, that is what it is. So, you are reducing. So, more and more energy gets settled down and then you get 0 kinetic energy, which happens at 0 Kelvin. Okay. So, here now you can understand when will an entropy be 0 for not any given substance, for a crystalline substance, it happens at absolute 0. Clear? What is absolute 0? 0 Kelvin. Okay. In the other words, at 0 Kelvin, the atoms in a perfect crystal are in complete order, because kinetic energy is 0. So, everybody settles down and there is only one possible microstate, thus entropy becomes 0. Delta S, when is it equal to 0, happens at 0 degree Kelvin. That is important and that is the third law. The third law has important implications for low temperature physicists, cryogenics and theoretical limits of cooling. Cryogenic is where they talk about machines, parts working at lower temperature than room temperature. The lower can be minus 25, minus 50, minus 100 degrees Celsius. That is what they are talking about, cryo, right. Cryogenic is low temperature. So, some people do cryogenic experiments. What they do is they try to take liquid nitrogen and then they try to pour it on top of a workpiece to study the response of the material. So, that is cryogenic. And if dry ice falls on your finger, it burns. Right. The law also implies that it is impossible to reach absolute 0 in a finite number of steps. How do I achieve? How many steps I do? Can I go from 25 degrees Celsius to 0 K in one shot? Very difficult. It is impossible to reach absolute 0 in a finite number of steps. As the substance is cooled closer to 0, it becomes increasingly difficult to remove additional energy from it. This means no real system can attain absolute 0 though it can approach very close to 0. So, 0 Kelvin is very hard to do, you will go close to 0 Kelvin. So, otherwise what happens is you see here minus 273. So, people talk about minus 50 degrees Celsius, people are also talking about minus 100 degrees Celsius. So, when do we get this minus 50 and minus 100? Of course, when you are at poles, North Pole, you can get minus 35 degrees, minus 40 degrees and all. But when you are traveling in a flight, when you go very high altitude, 30,000 feet, there the temperature will be minus 10, minus 12, minus 30, whatever it is. So, it is in minus. So, think of an aeroplane which starts at room temperature maybe 25, 30 degrees Celsius. As and when it increases its altitude, it can go up to minus 10, minus 20 degrees Celsius when it goes high up. And then from there it travels for a long distance and from there it settles down faster. The biggest problem is when you travel at minus, there is always a possibility that ice, if there is a droplet, that droplet gets converted into an ice and this ice can be a disaster for a plane. Okay. So, that is what people are very cautiously working, and look how amazing is the plane material used and the design. From a practical perspective, the third law allows scientists and engineers to define what is absolute entropy of a substance, not just the entropy change. I told you earlier in the lecture that delta S is very easy to do it, but S defining is very difficult, because delta S is from 1 kilometer to 2 kilometer, the difference is 1 kilometer. But you have to say this 1 kilometer with reference to 0, that 0 establishment in entropy is a challenge. So, that is what happens here. From a practical perspective, the third law allows scientists and engineers to define absolute entropies of substances, not just entropy change. This is useful in chemical thermodynamics, where standard entropy values are used to predict reactions, spontaneity, equilibrium and Gibbs free energy. These are very important. When we try to talk about Gibbs free energy, where does it come? It comes from the standard entropy. Reaction spontaneity, at what stage or what time does a reaction happen? The third law highlights an important boundary in nature. While energy and entropy are constrained by first and second law, energy and entropy are constrained by first and second law. The third law sets a theoretical limit on the minimum entropy and temperature of a system can reach. So, this is delta T equal to 0, delta S equal to 0. When delta T is greater than 0 and delta S is also greater than 0, you see this distortion happening to the atoms there. The third law also explains why material exhibits strange and unique properties at cryogenic temperature. So, at one point of time in early 1980s or 70s, people were talking about superconducting materials, right? And people were also talking about superfluidity. At that time, people are trying to do experiments and try to see what happens to the conduction behavior at low temperatures. Even now, a lot of people work on it, right? But the kickstart superconductivity was in 1970-80, it was peak. So, that room temperature. So, what people are trying to do is, when they see at room temperature, suppose if the conductivity is 10, right, forget units, right, 10x, whatever it is. Now, when they go to sub-zero, they see it can go up to 1000, just for discussion's sake, 1000x, right, and it goes down. So, now what they are trying to do is, they are trying to see whether I can create this ambient and keep the component there and see the conductivity is happening very fast. Conductivity, if it is happening very fast, the resistance is low. So, there is not much of heat dissipation. So, you can use the advantage. So, that is what is this. And superfluidity is also another major area which came into existence. So, that is why people are more interested to work with this third law. Though less commonly used in everyday thermodynamic calculation, the third law is essential to understand the thermodynamic behavior of matter at low temperatures and fundamental limits of cooling technologies. The third law finds critical application in various scientific and engineering fields at extremely low temperatures, we have seen, and the practical implication for the design of refrigeration systems, liquefaction of gases, storage of biological material with minimum entropy is crucial, right. Liquefaction is, you have a solid, you have a liquid, you have a gas. Suppose let us assume that you are having lot of natural gas available, maybe in the coast of Kerala, you have lot of gas which is available. Now, there is a deficit of gas in the northeast part, just for discussion's sake. So, then what they do is, the gas has to be transferred from here to there. One way is, you pressurize it and send a pipeline. The other way around is, they make individual containers, and these containers, what they do is, this gas is taken to a very high pressure and it is liquefied. So, that is what is called as liquefaction of gases. And once it is liquefied, then what do? Is they transport to that place whatever is required, and then that point it is again the pressures are released. So, then you get back a gas, right. And the storage of biological material is very important. That is why if you see, we always keep the food, once you finish your dinner, you put everything into the refrigerator, is because you wanted to maintain the food without any bacteria growth. So, that is why you put it into a refrigerator at 12 degrees, 14 degrees and it continues, right. In the same way, you can also store biological material. You have a tissue, it has to be moved, whatever. Storage of tissue where minimizing entropy is crucial. Overall, the third law is a powerful tool for understanding the limits of thermal process and plays a vital role in advanced technologies that rely on extremely controlled temperatures. Now, let us try to understand exergy. X plus energy, okay. It is called as exergy. Exergy represents the maximum useful work that can be extracted from a system as it comes into equilibrium with its surrounding. We are trying to represent the maximum useful work that can be extracted from a system as it comes into equilibrium with its surrounding. Energy is always conserved as per the first law of thermodynamics, but exergy is not conserved, it is destroyed in real process due to irreversibility such as friction, unrestrained expansion, mixing, heat transfer across a finite temperature difference and other inefficiencies. So, exergy is not conserved, it is destroyed. For example, you have a boiler, you have a complete system, right, this assuming that this is a complete system, you have a heat which is given, right. So, coal, like I was talking to you about the thermal power plant, you can also have gas power plants. So, there is a heat which is applied, there is boiler here. In the boiler, what happens is there is always water, this water is heated to a very high temperature. So, water gets converted into steam, the steam tries to move and then it is trying to operate a turbine. So, then as and when it moves a smaller, so you can, it need not be one attached to a shaft, one turbine blade, there can be a series, right. So, there can be a series which is there, so they rotate and then what happens, whatever this turbine blade rotation is attached to a generator, right. So, this generator is used to tap the electricity. So, now whatever is left out here, it comes to a condenser. What happens in a condenser? We try to condense the vapor into a liquid back, and then this, how, when you want to convert the heat into liquid or the steam into liquid, you have to extract heat out of it. So, you pass in a cold water and then you get this heat extracted and then you get the waste heat. So, water which comes out will be having lot of energy, in the sense it will be very hot. So, then the cold, whatever room temperature cold liquid is then taken and then there is a pump which pressurizes and again pushes into a boiler. So, this is how a typical thermal cycle works. This heat can be replaced by gas, then it is called as gas turbine cycle or gas power plant generation. So, if you look at energy flow, so it is chemical or nuclear energy, wherein which you have exhaust gas is there, the first coming out, then you have a hot stream is there, hot stream, thus you can remove the waste heat and then the rest you have motion, friction is there and then electricity is generated. So, this is how you have an energy flow and at regular events you tap out. Right. Now, let us see the exergy. Exergy flow is chemical or nuclear energy, whatever is used is here. From there you try to get an exhaust gas, then a hot stream goes, you get waste. From motion goes, you try to get friction and then finally you produce electricity. So, this is the difference between energy flow and exergy flow. So, exergy linkage of 3 E's. So, it is energy, exergy and entropy you have. So, it is always destroyed, entropy is always increased and energy is neither produced nor destroyed, always conserved. Okay. So, energy is doing this, exergy is doing this, always destroyed and then you have this. Exergy provides a measure of the quality or usefulness of energy, helping to distinguish between energy that can perform work and energy that is unavailable for work. So, this is what is a distinction it does. Exergy provides a measure of the quality or usefulness of energy, helping to distinguish between energy that can perform work and energy that is unavailable for work. You can clearly distinguish. It depends on both the state of the system and environment, typically defined by reference condition such as ambient temperature and pressure. Exergy. Type of exergy depends on the form of energy involved: thermal exergy, chemical exergy, kinetic or potential exergy. So, thermal energy is from heat, mechanical energy is from pressure, chemical energy is from chemical potential, kinetic or potential exergy is motion or elevation. The major benefit of exergy analysis is that it highlights where and how inefficiency occur in thermodynamic system such as power plant, engines, refrigeration and industry. The major benefit of exergy analysis is to highlight where and how inefficiency occur. So, that is why we always try to calculate the exergy. What is exergy going back? exergy represents the maximum useful work that can be extracted from a system, maximum useful work that can be extracted from a system as it comes into equilibrium with its surrounding. So, if you see here the energy flow, exergy flow, right. So, that is what it is. By identifying and minimizing the energy destruction, engineers can design useful systems. This makes exergy a powerful tool in energy efficiency optimization. It is especially valuable in modern applications such as combining heat and power systems, renewable energy integration and low carbon process engineering. So, energy tells us how much is there, while exergy tells us how useful that energy is. Please understand there is a big difference. How much is there, what amount of energy you have, what kilowatts you have. So, but while exergy tells you how useful that energy is. Unlike energy analysis, while many show the energy is conserved even in poor design, it shows energy is conserved even in poor design. Exergy analysis reveals losses, pointing out to the opportunity of improving performance and sustainability. So, if you are looking into sustainability, try to measure the exergy. While energy is always conserved, exergy is always destroyed in real process due to irreversibility. Right? Friction, unrestrained expansion, mixing, heat transfer, etc., etc. The energy of the universe, like its mass, is constant. Yet, at times we are bombarded with speeches and articles on how to conserve energy. What is not conserved is exergy, that is useful work potential of the energy. Once exergy is wasted, it can never be recovered. The second law, efficiency, a common measure on energy uses efficiency, is the first law, efficiency, NEX. The first law of efficiency is defined as the ratio of output energy of a device to the input energy of the device. The first law is concerned only with the quantity of energy and discard the form in which the energy exists. Quantity of energy, it discards the form in which it exists. It does not also discriminate between the energies available at different temperatures. It is the second law of thermodynamics which provides a means of assigning a quality index to energy. The concept of available energy or exergy provides a useful measure of energy quantity. I am sure with this and this you will be now able to understand and appreciate what is it. With this concept, it is possible to analyze means of minimizing the consumption of available energy to perform a given process, thereby ensuring the most efficient possible conservation of energy for the required task. The second law of efficiency, NEX, of a process is defined as a ratio of minimum available, very important, minimum available energy or exergy, which must be consumed to do a task, divided by the actual amount of available energy consumed in performing the task. So, this is very important. So, it can be represented by a formula in this way. Ex is equal to U. What is U? U is internal energy of a system minus internal energy of the environment. U minus U naught plus P naught. P naught and T naught are the pressures at the environment. V is the volume of the system. V naught is the volume of the environment. S is the entropy of the system, and S naught is the entropy of the environment. So, through this formula, you can try to find out the exergy of a closed loop system. Exergy is 0 when a system is in complete thermodynamic equilibrium with the environment. When it is now completely in equilibrium, it is 0. But in general, this is how the formula is for a closed loop system. So, this expression can also be interpreted as this way. Ex is equal to total energy minus the dead state energy. In the case of steady flow open system, this is for a closed system. This is for a closed system, non-flow process, right. So, this is for a flow process. X is equal to H minus H naught minus T naught S minus S naught. So, H naught is the enthalpy at a dead state and S naught is the entropy at the dead state, right. So, there are different types of exergy, as I told you: physical, chemical, kinetic, potential. So, physical is due to the difference in temperature and pressure, right, with the surrounding. Chemical is due to the chemical composition. It is usually obtained from the standard table of a common substance. So, kinetic energy is equal to V square by 2. Potential energy is Gz. So, the total energy is nothing but X physics plus this kinetic energy comes to this one. So, this is the total specific exergy is there. So, the exergy destruction and efficiency, the exergy destruction quantities are irreversible in process. So, Ex is equal to T naught into delta S G. So, delta S is the entropy generated. So, exergy efficiency compares actual performance to the ideal performance, useful exergy output divided by exergy input. So, the efficiency is always less than 1 even if the first law efficiency is high. So, the maximum useful work potential of a system at a specific state is called as exergy, which is a composite properties depending on the state of the system and the surrounding. It is always talking about system, surrounding, boundary, all these things: surrounding, system, surrounding, boundary. It always keeps talking about this only. So, the maximum useful work potential of a system at the specific state you already know is called the exergy, which is a composite property depending on the state of the system and their surrounding. The system which is in equilibrium with its surrounding is said to be at a dead state having 0 exergy. While the energy is conserved, first law, exergy is not. It can only be fully destroyed by irreversibility, making it a crucial tool for efficiency and sustainability analysis in real system. So, exergy is completely destroyed when the process is fully irreversible. In irreversible process, friction, unrestrained expansion, mixing of different substance, heat transfer through finite temperature difference, these processes generate entropy which directly causes exergy destruction. More irreversibility, more entropy generation, more exergy destruction. This is a thumb take home message for you. If more irreversibility, you will have more entropy, more exergy destruction. The system reaches mechanical or thermal equilibrium with the environment at the point when no temperature difference is there, no heat engine is possible, no pressure difference, no expansion work possible, no chemical potential difference, no reaction driven work happens. So, when there is an equilibrium, the system has no potential to do useful work. So, exergy is 0. It is said to be completely destroyed. Exergy is completely said to be destroyed. So, to recap, in this lecture, we saw what is a perpetual motion machine, how does a PMM interact with the first and second law of thermodynamics, what does a third law of thermodynamics imply. So, what does it say? Should we recollect and see what does it say? The law states that as the temperature of a perfectly crystalline substance approaches absolute 0, the entropy also approaches 0. That is what it says, right. So, we are trying to find out 0 of entropy, so that we can always have a relative measurement, a delta S measurement we can do. So, we saw that, then we saw about what do we understand exergy and what are its different types: mechanical, we saw chemical, this is what it is. How and when is exergy destroyed? So, these are the topics which we covered in this lecture. These are some of the references which we have followed. Thank you very much.